All right, so we'll kind of finish off the last kind of new material today. Might have some additional examples on Monday of it, but for the most part, we'll kind of have everything that will be on the exam kind of covered after today. Okay, we'll talk a little more about the exam on Monday, just kind of some more of the details kind of about it. But I do want to mention next Wednesday, we're supposed to have one of those study days where we won't be meeting. So going into the exam, I like to get a lot of review. So we're not going to necessarily you don't have to show up or kind of be synchronous, but I will post an additional video of me working through some of those practice problems. So I'll still post a video on Wednesday so that you have really just more review material to kind of go through. But we don't have, we won't kind of be meeting necessarily in class or kind of via Zoom. That being said, I'll probably still do it at the same time. I'll probably still start the Zoom link. I don't expect you at all to do it. It's just me, providing additional resource. So just wanted to put that out there before we kind of get started. Also, is kind of grading some of those Excel assignments. One thing I want to mention kind of moving forward is I need to see your work in the Excel file. So I don't know what the issue is, but when some of you uploaded some stuff, I can't see all your formulas, and I can actually, I can tell that you were using something, but for some reason, some of your cells, the formulas aren't showing up. Moving forward, I'm not going to give kind of full credit, even if the answer is right, if I can't see your actual work in Excel. Okay, kind of gave the benefit, the benefit of the doubt in this one. It's kind of our first one, getting used to it. Also, if you're working or kind of working with others, if I start seeing things that look really, really similar, especially when it's the written response and it's almost verbatim, I'm gonna call you out on that. So if you work together, that's okay, but make sure you're working on off of individual files. Okay. Other than that, I'm trying to think if there's any other housekeeping stuff to get out of the way. Does anybody have any questions for me before we get started here? Okay. So hopefully everything sounded good on Zoom. If it's not, kind of let me know. I can reset the audio, as that for some reason just appears to be a random issue. So we left off kind of last class. We worked through some Excel with that binomial distribution, and then we worked through examples as well. So we have another type of discrete random variable, which is called the Poisson distribution. Right? So it's kind of similar to the binomial, but a little bit different. So one of the examples we said that didn't work last week when we were saying which of these four don't work, it was one where we were looking at the number of errors made over a given week at the Muncie airport. So what we're going to be doing with a Poisson is we don't have a finite kind of capped number of successes that we could see. It's just going to be open-ended, and we're going to be looking at the number of successes over some space, right? Typically this is over time, but it can be over like a physical space, like over a mile, right? And this will make a little more sense as I kind of start working some examples, but we're going to try to find the probability that we see a certain number of successes over this interval, and then all these intervals are the same length. So this could be something like, what's the probability I see 3 accidents on McGalliard every week, or this week, right? My interval there is a week. I'm looking for my successes here are seeing accidents on McGalliard, right? The other kind of example, if we're thinking not about time, would be, if I'm walking down McGalliard, what's the probability I see 5 pieces of trash over the mile that I walk, right? So there it's not time, right? It's still space, but it's a distance of in distance space, right? So all the examples that I'll use on practice exams or on the actual exam, and even on the Connect, typically I'm always going to use time examples. I think today we'll get an example of what it would look like if we didn't use time. You can apply it to that, but for most situations we're going to be applying to the Poisson, we'll probably be thinking about time intervals. Okay? So it has to be true, and I'm never going to kind of try to trick you on this, but if we're thinking about there's all these different intervals, right? Each week is an interval. They can't overlap. So when we're looking at the probability of seeing 5 accidents a week, we can't, we're thinking about breaking it up into 52 weeks a year, not kind of overlapping weeks where we could look at, any 7-day period, okay? So non-overlapping intervals. And then we're looking for the probability that X takes on a certain number of successes over that interval. Okay? So, you know, we had a probability mass function for the binomial. We're going to have a probability mass function for the Poisson, okay? So it's a little bit easier in that there's not as many things to keep track of, first of all, but there's really only two things that we need to know, okay? So here, lambda, this Greek letter lambda, is going to be the average rate we usually see over that interval. So if I'm thinking about the accidents on McGallier example, maybe on average there's 3 accidents every week, okay? So that 3 would be our lambda. And then x is going to be, well, I'm interested in, okay, 3 is the average. What's the probability I see 5 this week? So x is still going to be the number of successes we're trying to find the probability of, right? In fact, you could almost think about, instead of f of x here, well, really, this is going to be giving us the probability x is equal to a certain number of successes. Oops, okay. The only other thing in this equation, I mean, we've talked about factorials, so we're okay with that now. Hopefully, you kind of see, you know, we have multiple examples here, so this is why it's important to figure out where that's at in your calculator, start getting used to using that factorial. But we also have this natural number e, which if you go out to the third decimal, it's like 2.71828. But it's kind of like pi, right? It's a number that's like pi, you know, that goes out infinitely. You know, if we're looking at this decimal point, you know, we could go way, way out. And so your calculators typically have this built in, right? So there's usually going to be some button. Usually it's like second, and then, you know, it's one of the things that are above all the kind of main buttons. But it'll kind of have that value stored in there for you. If you ever can't find it, right, you could use this out to the 5 decimal, and this is the value you should be plugging in for E, okay? But like I said, almost every calculator, even pretty rudimentary calculators have this, okay? So this f of x, I kind of already changed it here so we can kind of see it. It's going to give us the probability that we see a certain number of occurrences of whatever the success that we've defined over whatever other given interval is that we're looking at, okay? Any questions on this up to this point? Shouldn't be too bad. I think we've covered everything. So if we're thinking about an example here, and we'll get a look at that equation again. But there's just, I don't know, I'm not even trying to pronounce this guy's name, but he wrote this book that was pretty influential in mathematics and statistics called The Law of Small Numbers. So one of the examples that kind of comes from this book is he's realizing that in the Prussian cavalry every year, on average, 0.61 soldiers were getting killed by horses, right? Kicked to death by horses, right? Just accidents, okay? So what's the probability then, you know, I don't know, at the time, there probably weren't lawsuits, but you can imagine if something like this was happening in a factory where you know, you're having deaths, you might want to be prepared for lawsuits and you need the resources to do so. So you say, well, okay, on average, it's 0.61 and we can handle kind of those, but what if there's 3 people killed this year? What's that probability? If that probability is relatively high, we want to make sure we're prepared for that, right? If it's relatively low, then we're not as concerned, okay? So we're going to be looking for the probability that 3 are killed. So what are our lambda and our x? Well, on average, 0.61 soldiers were dying. So that's going to be our lambda. That's the average rate. And then we're interested in finding the probability of 3 people getting killed this year, or this is kind of, I guess more, but 3 our successes are if someone dies from getting kicked by a horse here, right? So we've got our x, we've got our lambda. This should be pretty easy, right? We're just plugging it in to the general form of that equation. And for some reason, I accidentally duplicated these here and didn't realize it. So you can kind of cross one of those out if you want to. So we're plugging in our lambda, 0.61, plugging in our x, which is 3. Now it's just a matter of kind of plugging that into our calculator. And we get a relatively low probability, and so maybe we're not as concerned about the number of deaths being as high as 3 this next year. Okay. Any questions on this? It's very, very similar process to what we're doing with the binomial. There's honestly just one less moving part. And, I guess we've got the E in here, which is a little bit different. But other than that, it's a pretty similar process. Okay? And all the same kind of principles would apply. And we'll get a look at kind of what, some of those principles of, well, what if I want to make it cumulative, or what do I want, things like that. So any questions at this point? I mean, it shouldn't be too bad just plugging our values in. Yeah.
Factorial, so you just put the number of occurrences.
So the factorial, so this, like 3 factorial would just be 3 times 2 times 1.
Okay.
So whatever the number of successes you're looking for, you just put that, kind of plug that in your calculator, and then put that exclamation point or that factorial afterwards. Yep. All right. So what if we had a slightly different example? So what if we wanted the probability, we're at a hospital. On average, we see that there's 1.25 births every hour. We want to make sure we've got enough staff on hand, though, because if, let's say, I don't know, if we only have 3 nurses there, we can handle kind of 1 or 2. But if there is 3 births, we're going to need an additional nurse on hand or additional doctor, whatever we're thinking about here. So what's the probability that we see 3 births in an hour given this average rate of 1.25? Well, the average rate is 1.25. That's our lambda. If we see the probability of exactly 3 births, we're looking for x is equal to 3. Just a matter of, same kind of thing, plugging those values in, right? Our lambda of 1.25, our x value of 3, and we should be able to kind of get this into our calculator and figure out the probability of 0.09 of that occurring, or a 9% chance, right? Which might be high enough to where we want to make sure we have, I don't know, somebody on call, right? Or maybe we just have someone there in case this 3rd birth occurs. So you can kind of think about, we're trying to predict these probabilities so that we can make better decisions or more optimal decisions for the future. Here's another example. I'm setting this up here. I'll probably go through this a little bit quick because it's kind of the harder stuff is kind of coming up. Right? So I think this isn't too bad, right? It's very, very similar to the last example. But what if I want to know what's the probability I see 2 or more births in this next hour? Okay? Well, to understand this a little bit more, if we just want to start thinking about what we're looking for, we have this average rate, right? So very similar to what we talked about with, I don't want to do that, sorry. Very similar to what we talked about with the binomial, I guess switched over here, is we can think about what this would look like visually, this distribution. So with a binomial, we said, whatever the mean of the binomial was, that's going to be the most likely outcome we see. And then as we move away from that, the probabilities are going to decline. The same thing holds for the Poisson distribution. So in this example, if we're thinking about x here, the lowest we can see is 0 births in an hour. Could see 1, we could see 2, 3, 4. It just kind of continues. Right? We don't have a finite stopping point. But if lambda is 1.25, what ends up being true for the Poisson is the mean is really easy to identify, because if the average rate we typically see is 1.25 births, well, that's the average, right? So if we see 1.25, we're probably thinking about 1 and 2 are going to be some of the maybe more likely outcomes, right? So when we see 1, maybe we see, I don't know, 2 is going to be close to it, or I don't know if it could be higher. I'd have to actually compute this, but they'll be the 2 most likely outcomes. But as we move away from that 1.25 mean, the probabilities start to decline, right? Start to get smaller and smaller. So you can imagine, this intuitively kind of makes sense. If on average I see 1.25 births in an hour, by the time I get to 10, that probability I get 10 births, really, really low, right? If the average is 1.25, it's very unlikely I'd see 10. So we're trying to find what's the probability, move this up here a little bit, of at least 2, so greater than or equal to 2. Right? So visually we're thinking about, well, we've got one of the more likely outcomes that is in this, fits this criteria, and then every other value above it. Right? So I doubt this is going to be a very small probability. Right? It's got one of the more likely outcomes, and it also has the majority of all the other possible outcomes we could see. Now, these 2 are going to be fairly likely outcomes, right? But they're not included, so it's not like we're going to be really close to 1. But I think one of the answers that was on that slide is like 0.03. Probably not going to be that low. Right? But if we want to go ahead and compute this, we're going to run into kind of a problem. So just like the binomial, I said, if we have one of these kind of greater than or less than signs, think about all the outcomes that meet this criteria and find the probability of each one of those outcomes and add them up. So here, probability x is equal to 2, plus the probability x is equal to 3, plus the probability, and it just keeps going. Where do you stop? Maybe theoretically, I guess the number of women within a certain age range in that around that hospital. But even if I can put a stop to it, it's a very large number. Every single time I want one of these probabilities, I'm going to have to use that Poisson distribution equation. This is going to be a lot of work. But if I remember, just like with the binomial, that we're really just looking for the probability of an event, A. So I can say that's the same thing as 1 minus the probability of A complement. Right? What would A complement be here? So if A is that it's greater than or equal to 2, A complement is that it's, yeah, just less than 2. Now, these are still discrete, so let's think about what outcomes would be in this, or would meet this criteria. Well, the very first one that meets this criteria is actually x being equal to 1. Yeah, right? Because there's no equality here. So the probability x is equal to 1 plus the probability x is equal to 0. We can't see, a negative number of occurrences of something. I can't have negative births, right? So I add, now I only have to use that Poisson equation twice, right? Add those up and subtract them from 1. So there's the same principle we talked a little bit about with the binomial, with this idea of using the complements, but it becomes really, really important for the Poisson because I literally can't find this, even if I wanted to do all the work. Where do I stop, right? Any questions on that before we keep moving here? Okay with that? So be really careful with these equalities, right? When I see less than 2, the first value that meets that criteria, right, was that x is equal to 1, okay? Because we've still got a discrete variable. So let's go share my screen here. Get rid of this. So like I said, one of the answers is 0.03. That's probably pretty unlikely, right? Because we had one of the most likely outcomes of 2, and then all these other values above it. So if we go ahead and we actually compute this, right, we need to find x is equal to 0 and 1. Plug the 0 in there, plug the 1 in, we get these 2 probabilities. We then would add them up and subtract them from 1. So we get about 0.35. Yeah. Oh, sorry. Thank you for saying something to me. I saw a confused look and I was like, okay. I wish it would be nice if I had like a back, like the projector had something back there so I could see what you guys are seeing at the same time. So right, all I'm doing is plugging a 0 in there into that Poisson equation to find that probability of seeing 0, a 1 in for x, adding them up and subtracting from 1. This is just the actual math. Right? Now, just like the binomial, one thing to remember here is anything to the 0 power is just 1. 0 factorial is 1. So really, when you're looking for the probability x is equal to 0, it's just e to the negative lambda. Because all this other stuff, multiplying and dividing by 1 doesn't change anything. Also here, dividing by 1 factorial, well, that's just 1, so I kind of ignore that. So just because I plug these values in, doesn't mean you have to enter exactly in your calculator what you have here. If you see these things that are just equal to 1, you essentially can ignore them because they're not going to change anything, right? Also, be careful when you're doing this, it's to the negative lambda. Okay? If you forget that negative sign, well, you're probably going to be able to figure out if you forget the negative sign because, let's see, I'll just pull up Excel to kind of show you. And also, I'm probably going to use it for something else later, so zoom, make it big. So if I do like, I think it's EXP in Excel. So this is like e to the power of like negative 1.25. That was the value we had in the slide, right? If I do e to the 1.25, I get a positive number. I'm looking for a probability, or a positive number, sorry. A number over 1, I'm looking for a probability. This doesn't make any sense, right? So if you forget the negative sign, you'll probably be able to figure out you forgot the negative sign, okay? All right. Any questions on that one before we keep moving here? Okay. I showed you something similar to this for the binomial last class. I think these are just nice graphs, but you can kind of see if we have a Poisson and the mean or lambda is really small, what that's going to tell us is, well, if the mean is 0.1, more often than not, what value am I going to be seeing? Remember, the mean is still like the average. Now, it'd be a weighted average, right? I would take the outcome of 0 times the probability that 0 occurs plus the value of 1 times the probability 1 occurs plus the value of 2, so on and so forth. But if I'm seeing on average 0.1, that means most of the time I'm going to see this outcome of 0, right? So 0 has a really high likelihood of occurring. And then as I move away from that mean of 0.1, the probabilities fall pretty quick. If I have a mean of 0.5, well, it still means I'm going to see a lot of zeros, but I'm also going to see quite a few ones as well. And then, 2, 3, 4, these become a little bit more likely here than they were before. If I see a mean of 2, well, that means 2 is going to be the most likely outcome, right? And then as I move in either direction from that mean of 2, the probabilities start to fall. Okay. Now, it's kind of weird here. Notice like 2 and 3 are, 1 and 2 are the most kind of have the same probability of occurring, even though the mean is 2. What we have to think about with a Poisson, it's always going to be right skewed, right? Because we're always censored at 0. We can't see anything to the left of that, but we can always see like an infinitely high number of successes theoretically. So remember the mean, I don't remember if we had a discussion in this section or it was the other one, but the mean is influenced by really extremely large values, right? So even though these have low probabilities of occurring, they're still going to pull the mean up a little bit. So even though the mean is 2 here, 1 and 2 are going to be kind of the equally as likely for us to see, because these these higher values are going to pull that mean up a little bit with the Poisson, because it's always this right skew distribution. Okay? Like I'm not even really showing you anything past 10, but theoretically there are probabilities associated with even all the outcomes past all the numbers of successes past 10. And then 5, we just kind of see same idea, right? 5 and 4 end up being kind of the most likely there. And then as we move away from that mean of 5, probability starts to decline. Okay? So unlike the binomial, the shape of the Poisson doesn't change with the mean. It does shift the distribution, but it's always right skewed. Right? Always has this long right tail. So we already talked about the mean is going to be equal to lambda, right? But a really interesting property about the Poisson, and you can kind of work through the mathematical proof. If I take this mean, I go back and I take the first number of occurrences, 0. I subtract that mean, or I subtract lambda. I square it, and then multiply it by the probability that 0 occurs. Then I add to that 1 minus the mean, or 1 minus lambda squared times the probability 1 occurs. I do that for every single possible outcome. I'm essentially calculating my a weighted variance there. And what ends up being true for the Poisson is you can prove mathematically that actually will always be lambda, right? So it's kind of a weird and unique property about this Poisson distribution, right? And when I was saying what's the probability 1 occurs, you'd be essentially plugging in that probability mass function. So everything just simplifies, and you're always going to have lambda when you calculate that variance. So it's kind of a nice property. And then to get this standard deviation, just trying to hammer this idea home. One more thing, square root, right? That's all it is, okay? So if we can calculate the variance, if we know the variance, we essentially know the standard deviation, right? All right, so that shouldn't be anything crazy. So yeah, just kind of this nice property. Actually, the further you get into mathematics, there's some situation where this becomes really useful distribution to use because it does have the same mean and variance, okay? Anything else I want to say here? I think that pretty much covers that. Any questions to this point? All right, so we'll work through another example. In this one, I'm going to relate the Poisson and the binomial. Right? So let's say I've got 10,000 atoms, and the probability that any one atom decays during the next minute is 0.0005. So what's the probability that we see exactly 3 atoms decay in this next minute? Well, we've got a time here, but we also have kind of this total number of trials. So we can apply the binomial to this because every atom has the same probability of decaying. Probability success is the same across every trial. I've got 10,000 atoms or 10,000 trials here, and I want the probability of exactly 3 of them. So my number of successes I'm looking for are 3. So I can plug those into my binomial distribution equation, right? N factorial divided by x factorial, n minus x factorial, so on and so forth. But this is these become, the decimal points, rounding starts to become an issue here if I am calculating this using the intermediate steps. And, even if I can cancel a lot of things, 10,000 times 9,999 times 9,998, it's still a really big value. And maybe if I'm not looking for the probably 3 decay, but like 9, maybe even my calculator, depending on what it is, can't even handle this, right? So, you know, it's annoying, even if I can find it, which I can here because enough stuff cancels. You know, maybe there's an easier way to do it. So a lot of the times when we have a situation like this, where we have a really, really high number of trials and a pretty low probability of success, we can actually, right, use the Poisson distribution, right? Now, it won't be the exact same probability, but it'll be a very close approximation, okay? So what I'll do is I'll use the mean of the binomial as the mean for my Poisson. So I calculate the mean for my binomial using n times p, right? And I just set lambda equal to that. Well, now, if I can find lambda, so there my n was what, 10,000, p was 0.0005. Excuse me. So we can kind of show that it's going to approximate that probability mass function, right? So I want to get to, here we go. So we get that lambda is 5, and we want to know what's the probability 3 atoms decay. Well, that's my x, so let's plug those into my Poisson. If I can, you know, this is a lot easier to deal with and a lot easier to get into my calculator, and it ends up being the exact same thing out to the 5th decimal, right? If I go out far enough, you know, some decimal point, it'll start to be a little bit inconsistent, right? It's still an approximation. But, that, you know, there's a hell of a lot easier in doing it the other way. Like I said, depending on what calculator you have available to you, right, it might be a little bit, you know, an issue with those factorials, even if we can cancel a lot, okay? I'm probably not going to like expect you to do this on the exam. I think there might be a question on the Connect. I can't remember if we ever have to do this conversion, but this is something, you know, important to know as we're, you know, moving forward in statistics, that sometimes, right, we can use other distributions as approximations. They won't be perfect, but they'll be really close. Okay? So let's think about a couple scenarios and then kind of figure out where we can apply the Poisson. And I think I have one more example that we'll work through that's not time, right? So let's say we're trying to figure out which of these is not going to work for the Poisson. So here, the first one, the probability that we see a certain number of accidents on a highway occur on a given day. Well, I've already used this as an example, so this one is probably maybe a little bit easy to figure out. We can use the Poisson here, right? As long as I know the average number of accidents, I could find the probability of any number of accidents occurring in that next day, you know, if I wanted to. So that one works. The probability of stock return exceeds 10% in a given year. Right? Well, this one looks like I've got a time interval, right? I've got this year, but what's the number of occurrences when I'm thinking about stock return? Well, only I'm seeing ever one stock return. It's just a different value, right? So it's not like I can say, what's the probability that a stock exceeds 10%? Well, it's, you know, it's just going to be a value. They're not in a certain number of occurrences. If I was like, how many stocks in my portfolio are going to return over 10%, that's a different story, right? But the way we have this here, this is not going to be a situation where we can apply the Poisson, right? The Poisson is we're looking for the same thing occurring a certain number of times. So like I said, this one we'd have to change to, you know, what's the probability that I see 5 stocks in my portfolio return over 10% or something like that. So that one's not going to work for us. So you can imagine these other two will. But we just talk through them. You know, what's the probability you get a certain number of calls in a call center in the next minute? We've got our time interval, right? We could look at past data, figure out what the average number of calls is. That one's going to be a pretty useful one to have the Poisson distribution. And then, you know, if we kind of more real world, what you might see in a job where we might actually use this. So yeah, especially if you're like doing, you know, any type of kind of insurance work, what's the probability we see a certain number of claims in the next month, in the next year, over the next week, right? We can use the Poisson distribution to figure that out as well. Okay? Especially you can imagine if there, or there's other things that might cost you large amounts of money and you want to know what's the probability I see it happen, you know, this many times, because I need to make sure I have, you know, the resources on hand to be able to pay that, right? And so I might want to be calculating probabilities of seeing, you know, a certain number of claims coming in or something like that. Okay. Where are we at? Oh, perfect. So I think Guinness Beer is the example that we have here. So there's this guy, W, I forget what his first name, I think it's probably William, but he was Gassette. So he was a brewer at Guinness, really smart guy, but he didn't have any education, right? And he was at he was there testing, you know, when they brew beer, they have these like huge, I call them vats. I know they're not vats. Someone else probably knows the correct terminology, but at these huge like silo looking things where they're brewing this beer. And you can't test every single like molecule within that vat to make sure it's, you know, advancing in the way that you want, but you can take samples from it, right? And what he noticed was as he was testing these milliliter samples from this large amount of liquid, he noticed that the number of particles, I think it was of yeast that he was seeing, followed a Poisson distribution. So he just kind of started, you know, he was writing down what the sample said every time, and he noticed, even though we're like, say, targeting, we kind of know what we're, the process that we're doing, we are getting about 10 yeast particles per milliliter in this vat of liquid. Sometimes I see an 8, sometimes I see a 9, sometimes, right? He noticed it followed the Poisson distribution. So he, made some other discovery. Once he got, discovered this, he then kind of also was looking at, well, I'm only looking at sampling, and he, student T distribution was kind of something he discovered. Well, why isn't it called the Guinness distribution? Why is it called the student T? Oops. Well, he made a bunch of money. That's why I put that on there. But, well, because he didn't have any formal training. And at the time, that was like a big, you just weren't given as much respect, right? So even the normal distribution is technically the Gaussian distribution because, a guy named Gauss discovered it. But here, everything that he came up with, they just kind of called the student distribution. Or so kind of using this as motivation. Right, let's say we have this large volume of liquid, right? This is like our we're not thinking about time now. We're thinking about some measure of liquid. So he's looking at milliliters, right? So this is kind of our interval. And he draws out 1 milliliter and sees the concentration is 10 particles. Or on average, he's finding that these samples have 10 particles of yeast cells in each milliliter. Right? So he knows the average rate in this huge volume of liquid because he just kept taking a sample after sample after sample and then found what the average was. However, now if we're doing a new kind of thing and I go in and I take one sample, what's the probability that I see exactly 8? Right? So I have the average, right? The average number of occurrences in this milliliter. On average, I see 10 yeast particles in a milliliter. So now what's the probability I only see 8 particles, right? 8 number of occurrences over that interval. The interval is not time now, it's like a volume, it's liquid. Right? So we've got our average, our lambda of 10. We're looking for the probability that we see 8. So lambda is 10, x is 8. Just plug them into that Poisson distribution, right? Nope, yeah, plug and chug, no pun intended. So, well, actually, I did intend it, right? But it becomes pretty easy, right? And this is something like, you can imagine if we were wanting to do, this is like a little more applicable, right? Because I could think of a similar thing where I can't test every product, but I can test some of them, right? Or if I'm thinking about a space, maybe I don't care about yeast particles per milliliter, but I care about tension strength over, a certain distance if I'm trying to go with like some type of steel beam that's supposed to support an entire building, right? So probably the space examples, and this is why, I don't give a lot of examples to you that are looking at this. It's probably really applicable to like engineering and things like that. But, it's used a lot, not with time examples as well. Just for most of kind of business-related kind of careers, you can think about anytime you'd really be using the Poisson is really going to be looking for number of occurrences over a certain time interval, more likely than not. So, but this is kind of a fun example where we can see it applied not to time. Okay. And if we plug it in, if we're trying to reproduce the answer just to make sure that we can get this entered into our calculator correctly, we get about 0.1126. And then, yeah, so I always like this meme. So have you heard the joke about the Poisson distribution? It's pretty fishy. Poisson means fish, and I always get this wrong. I think it's in French. But so I have this example, but I think we won't need all this time, and I kind of want to get at this today. So let's try to switch gears a little bit here. And I'm going to do this off the top of my head, so I might have to go to Excel to do some math for me here. So let's say that on average, excuse me. Actually, yeah. So let's say on average, I don't know. I think it's something like, in the US, I think it's something like 5 people die every year from getting struck by lightning. So it'd be very easy for me now to find, okay, what's the probability that 3 people get struck and killed this year, right? But what if I want to do something like, okay, what's the probability that I see X equal, what do I want to do? Like, let's say 2 people, but now I'm thinking about 2 people over the next month. Right? Well, I can't use this lambda, right? That's the average over a year. So what do I really want here is I want the average, or I want the lambda for a month. Right? So how could I get that? If I know that 5 people on average die every year, how many people on average die every month? Yeah, just divide by 12, right? There's 12 months in a year. So now that I have my new lambda, now it's really easy, right? Because I'm what 5/12 is what's 6? It's going to be some decimal. I can't think about this off the top of my head. But I'll just write it in there so you can kind of get this, right? So we've got lambda to the x, e to the negative lambda, divided by x factorial. Right? Now I can figure that out. So I had to make a conversion, right? And that conversion, if I'm going from a larger to like a smaller time interval, I'm going to have to divide by something, right? So kind of remember, if I want to go from if I want to go decrease the time interval, kind of think about you're going to be dividing by some factor. If I want to go from a week to a day, I would do what? I'd divide by 7. Right? If I'm going from hour to minute, divide by 60. Right? I'd never give you any example like this where you wouldn't know the conversion. And I think even when I do this on the exam, I put some things in there that probably some people seem very dumb, like there are 7 days in a week. Right? So I always give you kind of that, make sure we know what that conversion factor would be. What if instead I had an example where I'm thinking about, I don't know, every minute, I say the word 5 times or something like that, right? What if I then say, okay, what's the probability that I say the word I don't know, 100 times in the next hour? Okay. Well, I now need to update my lambda. I need the lambda for an hour. So if I know that I do, say it 5 times every minute, how many times do I say it every hour? I just simply take 5 and, I think you said it, multiply by 60. So if I want to go to a higher time interval, or my time interval is getting larger, right? In those situations, then I multiply by whatever that factor is, okay? And, there it's pretty easy. So what? Here we go. Lambda to the x, e to the negative lambda over x factorial. Now this might be an issue if I have something like this because I can't get this into my calculator. I was choosing these. I probably should have thought a little more about choosing my numbers here, but I was more so wanting to focus on kind of how we can convert to different time intervals here. Okay. Now all this assumes that it's equally as likely for it to occur in any given hour, right? And that in a lot of situations that might not apply, but in the ones that it does, we can do these conversions by simply multiplying or dividing that original lambda we were given to kind of translate it into this new time interval that we're looking at. Okay. Any questions on that? We're okay with that? All right. So go through this example. If we have a little bit of extra time, I do want to show something that I think would help with some of the homework. But I think this is a pretty interesting example. I always like statistics when it can kind of go against your intuition and kind of give you a result that you wouldn't have expected. Right? So let's say, this class I think is 40, but I use a class size of 35. One of my sections, the lowest section is 35. So imagine that we had 35 people. Imagine we could all be meeting at one time, right? So you have a room of 35 people and you say, what's the probability that at least 2 people in that room of 35 have the same birthday? So if you ask people this question a lot and you kind of give them these ranges, a lot of them are going to think it's relatively low, right? Usually, and when I have people in class, I always kind of use eye clickers here and we kind of look at the response and, but maybe because I'm bringing this up, you think, well, you already told me that it's counterintuitive, so maybe it's not low, right? But if you're asking someone, typically you would think, and I would think this is relatively low. I have 35 people, probably 2 of them have the same birthday, but probably pretty low, especially if we don't have twins, right? We're assuming that every day is equally as likely and that every single birthday is independent, right? So it's not like, making sure like you didn't have 2 moms trying to have kids at the same time so that their kids could grow up together, something like that. Right? So we could also figure out, at what point would the probability get over 50? Because if I have a room of 365 people or, 1,000 people, well, then the probability someone has the same birthday is, I would think someone has to, right? If you get 1,000 people together. So what is the kind of cutoff that gets us over that 50% point? So we can switch this around a little bit. If we think about the probability of X, oops, I have this on the other side now. The probability of X is just that 2 people have the same birthday. That's our event, okay? 2 or more. So if our complement of that would be that nobody has the same birthday, right? If X is that 2 or more people have the same birthday, X complement is that nobody has the same birthday, or every single person's birthday is unique. Right? So we'll do 1 minus the complement, or 1 minus the probability that nobody has the same birthday. Well, how can I figure out what that probability is? Well, I can find out that probably the first person has a birth date that's unique from everyone. Well, they're the first person, so that's not going to be very difficult. There's 365 possible days that first person could have a birth, or 365 days. All of them, we haven't looked at anyone yet, so the probability that the first person has a unique birthday, well, there's 365 days available out of the 365 days, so the probability is 1. And if I lined up everybody and I go to the very first person and say, when's your birthday? They're guaranteed they're going to have a unique birthday. The second person I ask of those 35, though, well, now there's only 364 other days that they could have a birthday on that wouldn't be the same as the first person. Right? So the probability they have a unique birthday is 364 out of 365. And the third person, well, now there's 2 days that they can't have a birthday on. So the probability they have a unique birthday is 363 days out of the 365. And I kind of continue to do this all the way up to that 35th person to get these probabilities. And if every single person's birthday is independent, if I want the probability that the first person has a unique birthday and the second person has a unique birthday, well, I'm looking for the intersection, but if they're independent, we said to find intersections, you just take the probability of those events and multiply them by each other. So I could multiply the probability the first person has a unique birthday by the probability the second person has a unique birthday times by the third, all the way down to the last person, right? And that would give me my answer. So that's what I have kind of right here. Right? So if we took all those probabilities, right, multiplied them by each other, we get the probability of that complement. Now we'd still have to subtract it from 1, remember, because what we were originally looking for was what's the probability that 2 people or more have the same birthday. So we figured, we plug this into our calculator, and what actually ends up being true is you can actually simplify this and solve this for any number of people, right? You would just be plugging in the number of people you're interested in right here, 365 days out of the year, and this equation actually ends up being the exact same thing as if you were to do it probability by probability. So we get about 0.186. We still need to subtract that from 1. So the probability that 2 or more people have the same birthday is actually above 80% in a class of 35 people. So I mean, you wouldn't think that, but it's, we can prove it with the mathematics right here. Right? And actually, if we want to go a step further, the number of people you need to get above 50% is actually just 23 people. Right? So if you have 23 people in a room and if you were asked to bet on this, the safe bet, right, just a little bit over 50% will be that 2 people have the same birthday, right? So this is kind of, I think this is fairly interesting. I always thought it'd be fun, like, somehow, I don't know, if you're in a room and you got like 50 or 60 people, I mean, with 35, it's already at 80%. So with 50 or 60 people, you're almost guaranteed that someone's going to have the same birthday. You could probably get a lot of people to take the bet that nobody has the same birthday and make quite a bit of money. I was always, I don't think I'm like keen or clever enough to ever do that, but that would be something that I always thought would be funny to do. Anyways, so this is a situation where we get a result that might not be intuitive. I just always think it's, these are always fun and interesting. And it really was using things we talked about before, right? Probability of intersections, just multiply by the probability of the events, right? If they're independent. And also using our complement rule, right, was part of this as well. Okay. I think that should cover it for us. Let me see, that was it, right? Yeah. I want to show you one other thing. Okay, before we get out of here. So I had a couple questions on this problem on the homework, and also I didn't really ever work through one exactly in class like this, so I understand where the confusion might come from. Let's say I wanted to find the probability that X was between 2 and 4. Excuse me. Well, I could find the probability X is equal to 2, plus the probability X is equal to 3, plus the probability X is equal to 4, right? But what I can also do is think about it this way. Let's draw a number line here. So let's go 0, 1, 2, 3, 4, 5. So let's just, I don't really care what these are. So I could find the probability that X is less than or equal to 4, which would be adding up all these probabilities, right? So let's say I have the probability X is less than or equal to 4. So it's something like, I don't know, 0.5. I then also have the probability X is less than or equal to 1. Right? Maybe this is, I don't know, 0.1. Okay? So if I were to take the probability of 1 plus the probability of 0, that's 0.1. If I take the probability X is equal to 4, 3, 2, 1, and 0, that adds up to 0.5. What I originally wanted was the probability that X is between 2 and 4. So what could I do here? Well, think about the outcomes that fit this criteria. 4, 3, 2, 1, and 0. So the only ones that I don't want to include from that list is the 1 and the 0. So what I could do, because this one includes the 1 and the 0, is simply take the probability X is less than or equal to 4 and subtract that probability X is less than or equal to 1, right? That subtracts out the 0 and 1 outcomes from this cumulative probability and leaves me with just 2, 3, and 4, right? Or, right, 0.5 minus 0.1 here. So it might be a problem that looks kind of similar to that, but you can use these cumulative probabilities to solve for something like this, right? Where you're kind of in a range in the middle. Most of the ones we looked at in class was either like less than or equal to or just greater than or equal to. So that might help you as you're kind of working on some of that, the homework problems, which I know they're due at the end of the week, at the end of the day, Friday next week, but I would try to start getting as much of those out of the way as possible because next week we want to be trying to start focusing and studying for that exam as well, okay? All right, if there's no other questions from me, I'll kind of let you guys get out of here. Make sure. All right. I will see you guys on Monday.